Good afternoon, everyone. This seismic image is from the thrust belt of northern Iraq. Note the structural complexity in the middle, associated with the lower Miocene compressional tectonism, followed by extensional tectonism. At two locations along the line, A and B, examine the semblance spectra and the accompanying SIP gathers from prestack time migration. From the semblance spectrum at location A, you can pick the RMS velocities with confidence. The presence of flat events in the SIP gather at location A confirms your velocity picks, whereas there is much uncertainty in picking the RMS velocities from the semblance spectrum at location B. And the SIP gather at location B does not clearly exhibit flat events. As such, it can be a futile exercise to use such a SIP gather for velocity updating and verification. Velocity uncertainty. Can we resolve it, or should we circumvent it? In relation to velocity uncertainty, there is one problem with CMP stacking as shown on the left. You fail to preserve reflection and diffraction amplitudes if you have erroneously high or low stacking velocities. Ideally, you would like to have a zero offset wave field as shown on the right, with reflections associated with gently dipping strata and steeply dipping fault planes and steep flanks of diffractions, all preserved. In relation to velocity uncertainty, there are two problems with prestack migration. You fail to preserve reflection amplitudes if you have erroneously high or low migration velocities. But you also fail to position the reflectors correctly and focus diffractions to their apexes if you have erroneously high or low migration velocities. You may choose to solve both problems simultaneously, as we currently attempt to do with prestack migration workflows, or you may choose to solve them one after the other, as we used to do in the 80s and 90s by workflows that included dip move-out correction. The quality of image gathers associated with prestack migration may or may not warrant the simultaneous solution. In areas with irregular topography, complex near surface, and complex subsurface, as in the present example, it may not. What then? The iCube workflow. The iCube workflow, applicable to both 2D and 3D seismic data, is designed to solve the two problems with prestack migration, one after the other, which includes synthesis of a zero offset wave field to capture and preserve all reflections and diffractions, followed by zero offset time migration. Back to the future, return of the DMO. As symbolically expressed by equation 1, the image in time obtained by the DMO workflow essentially is equivalent to the image obtained by PSTM, provided lateral velocity variations are within the bounds of time migration. Add dmig to both sides to get equation 2, where dmig stands for demigration, which is inverse migration. This means that the terms tmig and dmig on the left side of equation 2 cancel each other, and thus we get equation 3, Note that the left side of this equation yields the zero offset wave field given by equation 4. This means that as an alternative to the DMO workflow, we can obtain the zero offset wave field by PSTM followed by demigration of the resulting image. However, if you have committed yourself to an RMS velocity field with much uncertainty, the image from PSTM and in turn the resulting demigration would not be acceptable as a valid zero offset wave field. In fact, this was indeed the weakness of the DMO workflow. The iCube workflow instead does not commit you to a velocity field to obtain the zero offset wave field, and thus circumvents the velocity uncertainty and yields a valid zero offset wave field. The iCube workflow is in two parts. First, perform prestack time migration of shot gathers using a range of constant velocities and generate a set of image panels that form what we may casually refer to the migration cube. Use the cross sections of this migration cube to estimate an RMS velocity field. Second, perform inverse migration of the image panels in the migration cube using the same velocities as for PSTM and thus obtain what we may refer to the demigration cube. Sum over the velocity axis to synthesize the zero offset wave field with all the reflections and diffractions preserved. It can then be time migrated using the RMS velocity field as many times desired until the image is judged to be interpretively acceptable. Here are the three cross sections of the migration cube. The XT plane that shows the PSTM image for a given velocity, the VT plane that shows the semblance spectrum at a given CMP location along the line, and the VX plane that shows the time slice at a given time position. Take the opportunity to apply multi-channel signal processing to the individual image panels of the migration cube. Then perform inverse migration of each of the image panels using the velocities associated with the image panels. Subsequently, you may also wish to reduce the horizontal smearing on the VT panels. Applying this sequence of processes, you now have the panels of the demigration cube. Here is a subset of the panels associated with a range of velocities at constant increment. Now that we have constructed the demigration cube, sum over the velocity axis to synthesize the zero offset wave field and thereby preserve all reflections and diffractions that are present in the original recorded shot gathers. Here's an alternative display of the synthesized zero offset wave field. Now, you may justifiably raise the question, why bother with demigration, and why not simply sum over the velocity axis of the migration cube to get a velocity independent image directly, as shown here and as shown here, with an alternative display mode. Note that dipping events have been obliterated. This is because events in the migration cube are non-stationary, both in time and space. For the summation over the velocity axis to be valid, you need the stationarity condition satisfied, as in the demigration cube. Continuing with the iCube workflow, estimate an RMS velocity field from the migration cube and perform time migration of the synthesized zero offset wave field to obtain the structural subsurface image as shown here. The steep dips have been ascertained by the drilled well on the structural high. Compare this image with the image from prestack time migration using the same RMS velocity field. There are alternatives to simple summation over the velocity axis to synthesize the zero offset wave field, including weighted summation, extraction, and path summation. The path summation has been suggested by Evgeny Landa and Sergei Fomin, who applied it to the migration cube to obtain a velocity-independent image. Nevertheless, this approach suffers from the non-stationary problem, as we indicated earlier. As such, I asked Evgeny Landa to try the path summation applied to the demigration cube, as shown here, which turned out to be not much different from the result of simple summation over the velocity axis, as shown here. Now, can we improve upon this image by updating the RMS velocity field? Let us consider a structurally consistent RMS velocity estimation. Insert this image derived from the iCube workflow into the migration cube and pick time horizons acting like a structural interpreter and extract for each horizon the corresponding horizon consistent semblance spectrum. Pick the RMS velocity strand for each horizon and combine them with the time horizons to construct a structurally consistent RMS velocity field. Then applied mild smoothing to get the RMS velocity field, which you can then use to perform time migration of the synthesized zero offset wave field as shown here. This image using the updated RMS velocity field is really not much different from the previous image that we obtained using this RMS velocity field. Now this means that there is really not much need for any velocity update if you follow the iCube workflow. Now let us venture moving to the depth domain, but following a fast track. Perform Dix conversion of the RMS velocity field to obtain an interval velocity field, of course with some smoothing applied before and after Dix conversion. Using this interval velocity field, perform depth migration of the synthesized zero offset wave field to obtain the image in depth as shown here. Now I consider this depth image the interpreter's auxiliary image since we followed a fast track, whereas I consider the time image obtained by executing the iCube workflow the interpreter's principal image for structural interpretation. From this case study, you can infer my philosophy on imaging in depth in areas with irregular topography, complex near surface, and complex subsurface, which evolved over more than 2 scores of dealing with complex structures. I now express this philosophy by the following. Kronos gave us the arrow of time so that we may observe depths of the earth. But then others deceived us with the arrow of depth so that we may fall into our death. Exhausting, even futile can it be, pursuit for earth model in depth. When truly in need, wiser may it be to be content with earth image in time. Thank you for your attention. Please note that this presentation is but a condensed form of one small portion of the SCG webinar on land seismic data acquisition, processing, and inversion that I conducted beginning of March this year. The webinar audio-visual is now available online by the SCG. For details of this presentation, you may wish to subscribe to the SCG webinar.